Measurement of the mass of Saturn by Zishan and Joel. In this project, we will be using 6 of Saturn's moons, Rhea, Dione, Thetis, Mimas, Enceladus, and Titan, to measure the mass of Saturn. We are conducting this project mainly because of our interest. Secondly, it is important to know the mass of a planet when using gravity to assist spacecraft in gaining, reducing speed, and turning in the right direction. It is also due to the recent search of newly discovered exoplanets, such as KIC 7340288b, a potentially habitable planet. To know more about these planets, we can apply our method used in this project to find these exoplanets' mass.
Since we are not able to consistently use a telescope to view Saturn for 20 days, we have decided to use Stellarium, a space simulation, to record our observations. Every day at 6 AM and 6 PM, from 28th January to 16th February, by speeding up time, take a screenshot of Saturn and its moon. Using the screenshots, we put them into an online software, rapidtables.com, to measure the distance between the center of Saturn and each of its moons in pixels. There is also another method, called the projection method, where you draw the x-axis, or the east and west of Saturn, and the y-axis, or north and south of Saturn. Then, you project where the moon is vertically down to the x-axis and measure the distance from that point to the center of Saturn. However, this takes too much time and has too much room for errors that we decided not to do this. Take special note that when a moon's orbit has both noticeable inclination and eccentricity, and Saturn's angle of right ascension is also quite high, a different angle of view would alter the orbit's shape and semi-major axis, hence it affects the projection accuracy. Taking the average of a few tries, we then have a set of 40 data points for each moon. Step 2. Processing the data. First, we measured the diameter of Saturn in pixels. Then we calculated how much distance each pixel represents by taking the actual diameter of Saturn divided by the number of pixels. Then we converted all readings in pixels into meters. Next, we put all data points into a graph to find the orbital period of each moon. To find the orbital period, since the value b in the sine curve graph is 2 pi over the orbital period, we just took 2 pi over b to get the orbital period. Here we have an example of a sine curve graph for the orbital period of Titan. So why do we multiply by 2? Well, when we calculated the value t, we realized that their values were only half the orbital period values online. This is because our method was to only calculate the distance between Saturn and the moon at each point in time. This only worked because Saturn is facing us at an angle such that the moon's orbits look elliptical. In an elliptical orbit, there are 2 points along its orbit where the moon is closest to its planet. Therefore, we multiplied the value of t by 2 to get the actual value of t. Next, we cubed the semi-major axis and squared the orbital period and put them into a graph, and took the gradient of the graph and put it into the equation. Step 3. Calculation, results, and discussion. By putting the gradient through the equation, m equals to 4 pi squared m over g times 3600 squared, where m is the mass of Saturn, the smaller m is the gradient of the graph, r cubed against t squared, and g is the gravitational constant, 6.67 times 10 to the power of negative 11. At first, when we calculated the mass of Saturn, it had a 5.51% error from the online result. However, we realized that Mimas and Enceladus were anomalies of the graph, so we removed them and the error percentage improved to 4.71%. So why did Mimas and Enceladus have such a big error? Well, this is because of their small size and their close distance to Saturn, which makes them very susceptible to gravitational influence. The errors in our calculations resulted from number 1. Inaccurate measurements, 2. The moon's small size and orbit, 3. Orbital inclination and eccentricity, 4. Saturn's angle of declination and right ascension, and lastly, the second-order perturbation effects from other stellar objects.
On the bright side, calculations are within 5% error. Method is feasible to calculate masses of other planets. Depends on whether other planets have moons, perturbational effects of other celestial objects, moon's orbit inclination and eccentricity, planet's angle of declination and right ascension.
We would like to express our gratitude and appreciation towards our ISS teacher, Mr. Tan Ho Tek, for helping and guiding us through the project.